Kristen is a master's student in Zenwajia's lab. She has her bachelor's from North Dakota State University, and she plans to defend coming up in November. And she has a job at South Dakota State University. Congratulations, Kristen. She'll be starting soon. So good success story there. So Kristen, you should be able to share your screen. So go ahead and take over.
All right, thank you. So, as Craig said, I am Kristen Almen. I'm getting my master's in ECS program. My advisor is Dr. Shinhwa Jia in the Agricultural and Biosystems Engineering department at NDSU. And today I'll be talking about the impact of controlled drainage and subirrigation on water quality in the Red River Valley. So first, I just wanted to give a background of what tile drainage is for those who are unfamiliar. So the actual drain tile is a piece of corrugated plastic pipe that has slots in it for water to enter. So this picture is kind of shows the rolled up drain tile that you maybe see on semis going through interstate around town. And then it's, as it unrolls, there's like the single pipe, and then the tractor is hauling a tile plow where that installs the drain tile. So this is by Park River, North Dakota, which is about a 2-hour drive north of here. And so tile drainage is used in commercial settings, such as for draining parking lots. It's also used in residential settings, such as around the foundations of homes, and also in agricultural settings. So tile drainage is installed at a depth that lowers the water table. This is preferred by some people so that there's better growing conditions for crops, and there's more oxygen available to roots, and roots are able to grow deeper. And then it also provides drier soil conditions so that a farmer can get in a field earlier on, and that could in turn increase the growing season, the amount of time in the growing season. And then in the fall, if it's wet, the soil might dry out faster so that the farmer is able to get the crop off rather than waiting till the soil freezes, or maybe even harvesting the next spring. So tile drainage is needed in some areas just because certain soils are naturally poorly draining, or they may just have naturally high water table. Soils impacted by salinity can have some of these issues alleviated by installing tile drainage and then having a supply of water applied above ground. So this can help leach out the salts and over time hopefully alleviate some of the salinity issues. So water is often the limiting factor impacting crop growth. So once the adequate amount of water is applied to the crop, that can help improve yields. And as we all know, there's a growing population, so agricultural fields need to become more productive. So if fields that are currently in production can improve their yields by having drainage installed, that would be good. So here is like a little video thing of that same tile plow moving along. And then on the right is kind of like the spool of drain tile driving alongside. So it's installing the drain tile around a meter deep. And this is, yeah, still within the Red River Valley, but further north than here. And then this is what it kind of looks afterwards, how the practice of installing the drain tile kind of rips up the soil. And then you can kind of see the spacing that it was installed in this field also. So obviously, agricultural pollution is an issue in terms of surface water quality, and tile drainage is not an exception to that. So in terms of environmental side effects, the loss of nitrate and phosphate has been reported in multiple studies from tile drainage effluent. in terms of the farmer's perspective, it's very expensive to either, if the farmer wants to install it on his own, for him to buy, or him or her to buy the required equipment and then supplies and finding the time to do it, or they can have a company do it for them, which is also expensive. And then in dry years, there may not be any water leaving through the tile drainage outlets, so that can kind of have concerns in terms of, was the cost of installing it worth the maybe not even an increase in yield in dry years. But fortunately, there are solutions to these problems. So that outflow through the drainage outlet can be controlled, and irrigation can also be applied back through the drain tile. So in terms of the environmental impact, if there isn't any drainage outflow, there isn't any impact to surface water. So only draining when desired is known as controlled drainage. So this usually involves just having a free drainage before planting and harvest, so that the soil can kind of dry out and equipment in the field doesn't get stuck. And then pumping water back through the drain tile is known as subirrigation. So when these practices are combined, it has been shown in some studies that the crop yields have improved. So this first picture is the drainage outlet at the Fairmount site that I'll talk about a little later. So the outlets for the drainage systems can either be just with gravity, so the water just flows out kind of on its own, but there has to be enough of a change in elevation at the outlet for that to occur. But at this Fairmount site, that wasn't the case. So the farmer had to install a sump pump to lift the water up and out of the field. So that's what's shown there. And then, so this site does practice controlled drainage simply by turning off the sump pump when the farmer doesn't want drainage outflow to occur. And then also in this picture, this is the setup for sub-irrigation, where groundwater is pumped up and then applied through the drain tile. The second part that I'll talk about deals with the site in Clay County, Minnesota. So this site, the drainage outlet did have enough of a change in elevation to have a gravity outlet, but to perform controlled drainage, the farmer split the field into 3 sections, and then each section drains into one of these control structures. So within this control structure, there are stop logs that can be either stacked or removed. So if the bottom of the structure doesn't have a stop log, it'll basically be free drainage. But if desired, the farmer can stack up those stop logs so that it would take a great deal of water to actually flow up and over them. So it'd be basically practicing controlled drainage. And then here is a photo from above of the sub-irrigation setup for the Clay County site. So instead of using groundwater, the source for sub-irrigation at this site is the drainage ditch north to the field. So the same ditch that receives water from the control structures is where water is pumped out of and then into that bin and applied through sub-irrigation when desired. So this field's considered to practice drainage water recycling also. So as I said, the first part of the thesis deals with the Fairmount, North Dakota site, which is in the way southeast corner of North Dakota. The years of data available were from 2012 to 2018. That is focused on this section. And as I said, this field has controlled drainage with that sump pump that's turned off for certain periods of time, and then sub-irrigation where groundwater is the source. And this section focuses mainly on water quality. The second section, as I said, was in the Clay County, Minnesota site. The years of data that we looked at are from 2013 to 2019. And this site also has controlled drainage, but with those 3 control structures, and then the drainage water recycling, where the water from the ditch is used for irrigation. And this section deals a little bit with water quality, but also there is an undrained field and a free drained field. nearby this field with controlled drainage and subirrigation. So we were able to compare some aspects between those 3 fields in that section. So first, for the Fairmount site, here's the experimental layout. So the elevation is shown, and then the tile spacing is also shown. So you can see that the field is divided into 2 sections. Each drains into its own sump pump. So the water samples that were taken that are discussed are from that east sump pump, and then also from the west and east end of that drainage ditch north of the field. And then soil samples will also be discussed, and you can see where those are located kind of randomly throughout the field. Some of the questions that we're looking at answering in this section were to compare the water samples that we took to the North Dakota surface water quality standards and seeing if any of the concentrations were above recommended values. We wanted to look at if there were any differences between the upstream and downstream ditches. And if there were any, we thought that would probably be attributed to the field site in question, since that's the major contributor of water to this ditch between those 2 sites. And then finally, we looked at the impact of subirrigation on water and soil quality. So it had been previously reported on a paper dealing with this field that the water for subirrigation was of marginal quality, being that the EC was between 1 to 2 decisiemens per meter and the SAR was between 4 and 6. So we were interested in if that had an impact on the water drain from the field and on the soil near the tile. So the water samples were collected bi-weekly from the 2 ditch sites and then the east sump pump, and they were analyzed at the North Dakota Department of Environmental Quality. And then with that data, we split it into the management practice it occurred during. So it's free drainage spring, where outflow was occurring, controlled drainage spring when the sump pump was turned off, subirrigation when the water wasn't, drainage outflow wasn't occurring and subirrigation was being applied, and then controlled drainage fall. And so the sump pump is still turned off, and then free drainage in the fall when the drainage outflow is occurring. So this was able to tell us like when the sump pump was impacting surface water, and then we'd also be able to see how the water samples changed during subirrigation, and if they did because of that different water source, the groundwater. To allow for nutrient load calculations, the drainage outflow was measured at the sump pumps. So we had the daily drainage outflow volume, and using that along with, so interpolating the nutrient concentrations for daily nutrient concentrations, we were able to calculate the daily nutrient load. And then the soil was sampled above the drain tile. So in 2014, 2015, and 2017, soil was excavated above the drain tile, and then these samples were analyzed at the NDSU soil testing laboratory. So first up, we'll talk about the water samples from the east sump pump. So as expected, the samples taken during the subirrigation period were significantly different than the samples taken during the other 4 management periods. So you can see that the percent sodium was quite a bit higher, the SAR was higher, and then the phosphate was also a little bit higher during this period. The values that were above the recommended values by the North Dakota Surface Water Quality Standards are in those red boxes. So you can see that the percent sodium during subirrigation was supposed to be recommended to be below 50%, but here it's at 63.6. The sulfate concentrations during free drainage spring, controlled drainage spring, and free drainage fall were above the recommended concentration of 750 milligrams per liter, though sulfate is just dominant in this area, so we kind of expected the concentrations to be high. And then the nitrate, nitrite, nitrogen and during free drainage spring was above the recommended value of 10 milligrams per liter. But it's important to note that, so this is data average from 2012 to 2018. But if the 2012 data was excluded, that concentration would be below 10 milligrams per liter. So we thought the 2012 data showed higher concentrations than usual because more drain tile was installed in the field in 2011, and it can occur when the first year the drain tile is running that some of those concentrations are higher than they will be in future years. So here on the top is the samples taken from the upstream site, and on the bottom are the samples taken from the downstream site. It's once again the averages from 2012 to 2018. So once again, the sulfate values were above that recommended 750 milligrams per liter for all of the management periods and at both sites. But in terms of trying to determine the impact of the field on these samples, neither the upstream and downstream sites or within those sites and between management practice periods were there significant differences. So then we looked at the nutrient load. So first is the nitrate, nitrite, nitrogen. So on the top, it's the cumulative load in kilograms per hectare. And then below shows just the amount of drainage outflow that occurred in that year. So you can see that 2013 had the most drainage outflow with 107 millimeters, but 2013 was not the year with the most load. In this case, actually 2014 had the highest load. So, and then when I plotted the nitrate, nitrite, nitrogen loads against drainage outflow, the R-squared was only 0.56. So it showed that they weren't as correlated as you'd think. It's kind of expected that if the more flow there is, the more load, but so it showed that maybe the concentration had a higher influence on the nitrate, nitrite, nitrogen load than drainage outflow. And then, so the highest load occurred in 2014, and it was 10.9 kilograms per hectare. So I also found a study in Manitoba where they had a similar amount of drainage outflow, 53 millimeters compared to our 56 millimeters. And they reported an end load of 10 kilograms per hectare. So it was fairly similar. Next, we looked at the phosphate load. As you can see, there's only 2 years of data available. The concentrations from 2012 to 2016 weren't available. But this time, so 2017 had 12 millimeters of flow, and then 2018 had 6 millimeters of flow. So you can see that there was a positive relationship between the flow and load with phosphate. So this R-squared was above 0.95. So maybe showed for phosphate that the flow had more of an influence than for nitrate, nitrite, nitrogen. So using that same Manitoba study, so they reported a phosphate load of 0.08 kilograms per hectare, but this is when there was the 53 millimeters of drainage outflow. So assuming all things are equal, and if they only had 12 millimeters of outflow, that same phosphate load would be 0.02 kilograms per hectare, which is once again fairly similar to what we found. And so the last load we looked at was for total dissolved solids. So we included this despite the fact that it doesn't indicate the specific contents of the dissolved solids. It can be used as an indicator of conductivity, and it's often used as a water quality parameter. So like the phosphate, this data also showed that the years with the most drainage outflow had the most load. Yeah, so you can see that 2013 had the highest load, and that's the year where the most drainage outflow occurred. So finally, we looked at the soil in response to the subirrigation and drainage. So the table shows data from 2014, 2015, and 2017. And the rows are broken into the distance above tile that the soil is sampled in. So there is from 0 centimeters, 20 centimeters away, 41 centimeters away, and then 81 centimeters away. And so this is the average of those 3 samples taken from those 3 sites from the experimental layout also. So pH was measured, EC and SAR were all measured. So prior to looking at the data, we expected the EC to be lower as you got closer to the drain tile. We thought this because the leaching of salts through drainage, but because the SI sub-irrigation water had some sodium related issues, we expected the SAR to be higher closer to the drain tile. And you can also see on the right, I included the table of the total precipitation, which is the sum of rainfall, the snow water equivalent, and sub-irrigation. And then the sub-irrigation is also given to the right of that. So you can see kind of the portions of total precipitation that were made up from sub-irrigation each year. So looking at the 2014 data, you can see that the SAR ranges from 1 to 1.6 about, and it increases as you move away from the tile. But in 2015 and 2017, the furthest samples taken the furthest distance from the tile actually showed the lowest SAR values, and the values at 0, 20, and 41 centimeters away rose to between 3 and just over 4 for the SAR. And then the EC didn't really show that clear of a pattern in terms of the changes. So we kind of thought that over time, if the total precipitation was made up more of sub-irrigation, that this could have led to more severe impacts in terms of soil quality. But at this moment, for soil to be considered sodic, the EC is supposed to be below 4, which it was, but the SAR is supposed to be above 13, which it was fairly far from. So at this moment in time, there weren't severe impacts to the soil, but it's not out of the question if the farmer had applied sub-irrigation more rigorously in the future. So to wrap up the Fairmount section, the water samples taken during sub-irrigation were found to be significantly different from those taken during other management periods. The chemical loads were similar in terms of the phosphate and nitrate to those in areas with similar amounts of drainage outflow. And the SAR values did increase over time near the drain tile, but the SAR value is still well below the level associated with sodicity. But we predicted that greater impacts were likely if sub-irrigation was used as the main water source for the field. So next I'll talk about the Clay County site. So as I mentioned, there are those 2 other fields along with the controlled drainage and sub-irrigated field, which is outlined in black here. Outlined in red is the undrained field, and then outlined in blue is the free drained field. So you also given is the tile spacing for the free drain field and the sub-irrigated and controlled drain field. So you can see that the tile spacing is a lot closer. The field outlined in black to allow for sub-irrigation. Also given are the locations of observation wells used to monitor water table depths. So those are the pairs of blue circles in all 3 of the fields. And it's also important to note that the soil series present in these 3 fields were fairly similar. And then the drainage ditch is also shown in blue. So water samples were taken from the west end and east end of this ditch. And then in the middle, that star represents where the sub-irrigation tank is, where water is pumped out of the ditch for sub-irrigation. And then very close to the west end of that ditch is where the control structure that receives water from the sub-irrigation and controlled drainage field is. So things we looked at For this section, we're to see the response from the water table to a rainfall event and comparing what that would look like for all 3 fields using data from those 6 observation wells in each field. We also wanted to look at the differences in water quality between the surface runoff collected from the undrained field and the subsurface drainage water from the free drainage outlet and within that control structure. And then finally, we looked at how the crop yields compared to each other between those 3 fields and compared those to county averages. So water samples were collected weekly from the control structure and both ends of that ditch. And then surface runoff samples were collected when there was visible water from the undrained site and the free drain site. And then free drainage outflow samples were also collected when that was flowing. As I said, the water table depth was measured within those observation wells. And then so that we could kind of see a response to a rainfall event. And since water samples weren't collected very often from the undrained field, just because the chances that there would be water there once a week was kind of slim, so that we just chose samples taken from June 24th of 2015 and compared the water samples collected. And then also there was a rainfall event on the evening of June 24th, so we were able to look at the changes in water table depth between those 3 fields. And the yields were just reported by the landowners responsible for the fields. And then the average Clay County yield for the specific crops I obtained from the National Agricultural Statistics Service. So here is the graph showing that change in water table depth. So on the x-axis, each tick mark is 6 hours. So it starts at 12 a.m. on the 24th of June and it ends at 12 a.m. on the 26th of June. And then for the first y-axis, it's the water table depth in centimeters. And then the other side is the rainfall just in millimeters. So the red line represents the undrained fields, the averages of the 6 measured water table depths. And then the black is the field with sub-irrigation and controlled drainage. And the blue is the free drain field. So you can see that all 3 of the responses were fairly different. The undrained water table rose about 40 centimeters and actually came fairly close to the soil surface. And this also had the most rapid increase in depth. It's important to note that this is the depth measured every half hour. The field with sub-irrigation and controlled drainage had the second highest increase, though it's still far less than that from the undrained field. And it actually kind of hit a peak and then started decreasing. And then the response to the free drain field was much more gradual than the other 2 fields, and it increased in depth the least, I guess decreased in depth. And so here is drainage outflow measured from the free drain field and the field with sub-irrigation and controlled drainage. So this also was fairly different. The free drain, so I guess this is pretty much where the rainfall event occurred. And you can see that the free drainage outflow doesn't really seem to respond to that rainfall event. It kind of just goes down in outflow over time. But in contrast to that, the sub-irrigated and controlled drainage field all of a sudden kind of had a lot of outflow. And so this we think represents the amount of water it took to flow over the stop logs within that control structure. So then we looked at the water samples that were taken on June 24th. So we looked at the nitrate, phosphate, and EC, and samples were taken, as I said, from the control structure, from the undrained field's surface runoff ditch, from the free drainage field outlet, and then at both ends of the ditch once again. And then the control drainage and subirrigation control structure column is in bold to indicate that drainage outflow wasn't occurring at that time. So as you can see, the phosphate concentrations were fairly different. For the surface runoff ditch, it was actually at 1.39 milligrams per liter, but for the control structure and the drainage outlet, it was only at 0.04 and 0.05 milligrams per liter. And we expected this to be due to the presence of soil in surface runoff. And so since phosphate binds to the soil particles, if there's more soil, we're expecting higher phosphate concentrations. And then when comparing the upstream and downstream ditch, you can also see that the phosphate concentration increased quite a bit there also. But in contrast to the pattern that phosphate showed, the nitrate concentrations for the control structure and the drainage outlet were much higher than that from the surface runoff ditch. And we attributed this to the higher solubility of phosphate, or of nitrate, sorry, excuse me. Yeah, so in subsurface drainage water, there'd probably be more nitrate than surface runoff. And then when looking at the upstream and downstream ditch, the nitrate, once again, the nitrate concentration increased again. So here, I know this is a lot, but it's the yields for each year for all three fields. So like the other figures, the blue is free drainage, the black is subirrigation with controlled drainage, and then the red is the undrained field, and yellow represents the averages reported from Clay County. So on the left is the corn yield, and the y-axis is from 0 to 200 bushels per acre, and then the middle is soybean yield from 0 to 60 bushels per acre, and then on the right is the sugar beet yield from 0 to 30 tons per acre. There was only 1 year where sugar beets were planted in the field with subirrigation and controlled drainage. So to try to kind of make sense of this, I determined the percent either higher or lower each field's yield was compared to the Clay County average. And then I plotted that against the total precipitation from each year. And surprisingly, the field with subirrigation and controlled drainage really was the only one that had any sort of correlation somewhat, so that the yields were higher in yields in years with the most precipitation. It was kind of surprising that years with more precipitation, the undrained field, we would have expected to have lower yields, but that wasn't necessarily the case. And the free drain field didn't really show any patterns in relation to precipitation either. Oh. And then the free drainage field's yields were overall the highest, followed by the field with subirrigation and controlled drainage, and then the undrained field. So the only year where the same crop was planted in all three fields was 2017, when corn was grown. So you can see that the three fields were higher than the Clay County average, but actually the lowest out of the three fields was the field with subirrigation and controlled drainage, followed by the undrained field, and then the free drain field actually had the highest yield. So to wrap up the Clay County section, it was shown that after a rainfall event, the undrained water table rose the most, followed by the field with subirrigation and controlled drainage, and then the free drained fields water table. And it was also important to note that the water table within the undrained field actually came fairly close to the soil surface, so this likely had some impact on crop growth. We showed that the phosphate concentrations were much higher in the surface runoff sample compared to those taken from the subsurface samples from the control structure and the free drainage outlet. But the nitrate concentrations were found to be much higher in the subsurface drainage samples compared to the surface runoff sample. And then the free drainage fields yields were overall the highest, followed by sub-irrigation and controlled drainage, and the undrained field had the lowest overall. It was also interesting that the amount of precipitation most closely correlated with the sub-irrigated and controlled drainage yields. There was not much correlation between the free drained and undrained yields with precipitation. So before ending, another part of my thesis has been some work with a drone. So I've been tasked with making 3 educational videos on how a farmer can use a drone and to just describe the practices of controlled drainage, sub-irrigation, and drainage water recycling. So earlier this year, I made an update video for a transforming drainage meeting, and I just figured I shortened that down to give you guys just a little taste, I guess, of what I've been doing with the drone. So here it is. So this is at the Clay County site, and that has the controlled drainage and sub-irrigation. And the drone you have is a DJI Mavic 2 Pro. And this is just the camera that came with the drone. So we weren't really doing anything fancy, just being able to have another view of the field. So the first thing we showed that we can do with the drone is to monitor snow melt. So this is from April 7th of this year. So as you can see, there is still quite a bit of snow on the field, but some soil visible. And then there was some water present in that surface drainage ditch. You can see it kind of shine there. But then we went back just 3 days later, and there was really not much snow, and still some water present in that surface drainage ditch, but really not much. And since that undrained field is so close to the field with controlled drainage and sub-irrigation, so this is still April 10th, and we're able to look at the undrained field, and you can see that there's a lot of surface water present. I'll pause it. So yeah, kind of it shows how beneficial having tile drainage can be in the spring, and how this would probably likely translate to a later planting date compared to that other field. And then, so this is just west of the field with controlled drainage and sub-irrigation. Over that road, there's a river, and this is on April 10th still of this year, and you can see how the river went out of its banks, and there's a flooding situation. So the drone gave a nice view of that also. And then I went out on July 3rd of this year and looked at the crops. So the farmer had grown sugar beets. And so yeah, then this is later in August. You can see kind of the differences in how the crops look. And yeah, I kind of crash landed one time, but I didn't break anything. So the goal kind of the videos is to just show that the video collected from a drone gives a lot better view of what's going on in the field in terms of like the crop growth status and moisture status, snow coverage status, compared to just standing on the side of the field. You really can't get a good picture of what's going on in the field. So and then I guess if I can fly a drone, a farmer probably could too. So hopefully it encourages farmers to try to use some more tools to be successful. So yeah, here are my acknowledgements. Definitely thank you to Dr. Gia, my advisor, Dr. DeSutter, and Dr. Scherer, and Dawn and Talon and Raina and Uday. Really enjoyed working with all of you. I'm sorry I ask you for data all the time, Dawn. Thank you for not getting mad at me for that. And here's all the funding. And here are my references. And thank you all for listening. And if you want to just email me questions that come up later, here's my email, but I'd be happy to answer questions now also. So thank you.
Thanks, Kristen. I see some claps there. If you want to unmute yourself and ask a question, go ahead, or put it in the comment frame. I'll start, Kristen. This is a little bit toward the end. You talked about flooding, and so if there were cooperative agreements between the city of Fargo and farmers, it seems like those control units could be put into place to limit the rate of contributions to flooding. Whereas with a free drain systems, that wouldn't be the case. Is that, first off, is that true? Would that be one way to manage the contribution of snow melt on fields to flooding in the Red River?
Yeah, so, and really the sump pump outlets are fairly common here. So anyone with that would have the ability to practice controlled drainage when requested. So I know there's like a flood control concept of like the waffle concept, where each field is like the dip in a waffle, so that a farmer is holding in or not allowing drainage in his field by turning off the sump pump. So that's holding in water. But I mean, if I'm a farmer, I want to be able to dry it out fast too. So I guess there's definitely different sides of that issue, but in theory, yeah, that would maybe help in the spring.
Yeah, it seemed just during high snow years that if there was a almost like a conservation reserve program where the city could pay farmers to, because their yield will drop, right, if they don't start as soon as they can. So okay.
Yeah.
And you got at this a little bit, but it sounds like I never realized that the tile can also be used to irrigate back. And so that's coming directly out of the ditch, or do they ever tie into pumping up groundwater to irrigate?
Yeah, so that's what they're doing at the Fairmount site. Another option is to kind of construct a pond and use that for irrigation. So, and that could be where the field's draining into that pond, but also water is being pumped from that pond back to the field. But obviously that takes quite a bit of area to hold enough water to make a difference. But yeah, there's different options for where that water comes from for sub-irrigation. Yeah, but it's definitely kind of puts the farmer in the driver's seat in terms of if they want water, they can have it. But if they want to get rid of water, they can do that too.
And I have one last question. I'm not seeing anybody with questions yet, so sorry about that. In terms of how much area is not, how much drain tile is there in the landscape? I mean, it seems like it's gone up tremendously in the last couple decades. Is that true? Are there very few undrained fields?
Yeah, so I think I have this written down somewhere, but in terms of like the permits given out in at least Richland County, North Dakota, which is like the southeast county, I think since like 2006, the number of permits went up like 586% or some crazy number. So yeah, it's definitely becoming more popular in the Red River Valley now. The pictures I showed are up in the north where it's not as common, but it's definitely gaining popularity. And like all of Iowa and Indiana, those states have it. A lot of their land is already has drain tile, so this is kind of an area where it's slowly gaining popularity and becoming more common. So,
is it subsidized? Are there subsidies from the federal government that help pay for drain tile installation?
not that I know of.
Okay. We'll just be patient, just like we are in
Okay.
class.
I mean, I guess this is better than hard questions or no questions.
Dangling.
I've got a question.
Okay.
So you were talking about how like the nitrate and phosphate runoff amounts were different with the different types of drain tile or like water management. So
Yeah.
why would those be so different from each other?
So are you saying like the surface runoff versus the subsurface?
Well, just like why would the nitrate concentrations and phosphate concentrations not kind of move with each other?
Okay, sure. Yeah, so there's a lot more soil in surface runoff, so that's being carried with the water, but really there shouldn't be much soil entering the drain tile. So if the phosphate is kind of tied to that, that's the soil particles, and then also the nitrate is more soluble, so that if there's more soil versus the water present, the nitrate will be more prevalent in the subsurface samples. But yeah, I guess it's kind of confusing. And it's also important to note that with tile drainage, it's not, well, versus controlled drainage. So we didn't really expect differences between the free drained and the controlled drained. So it's reducing the nutrient loads rather than changing the concentrations. But yeah, it was still interesting that the controlled drainage nitrate concentration was a lot different than the free drainage nitrate concentration. So
We'll not see any more questions. Kristen, thank you. See, people are lighting up their clap. So, and good luck with your defense and especially your new job.
thanks.
And everybody else have a good week and let me know if you need anything from me.
Thank you.